Full disclosure, I did not finish making the slides because there were no slides, and I thought this was a normal length chapter, and so we have slides for a lot of it, but we don't have slides for the end. If we get there, I'll just switch over to the chapter. But I don't even know if we'll get there because it's really long. Okay, so let's go. Oh, thanks, Gabby. Yeah. All right. So we are doing a case study today. And the general idea of this chapter is that we're going to be, oh, sorry, okay. Hi, everyone. My name is Kaija, and I'm presenting the case study chapter of the ggplot2 book today. I always forget to do that. Okay, so today we're going to be talking about a case study where we're going to apply the lessons from the previous chapters to write like a full extension for ggplot2. And so we're going to be talking about stats and geomes and grobs and different sort of the different uses of each of those things and sort of what the limitations are. And I really liked this chapter because it instead of just telling us in theory when we might need to use one thing or another, it actually leads us through and has us encounter the problems in real time. You do it one way and then you encounter a problem, do it another way to fix it, and then encounter a problem, et cetera, et cetera. So very realistic. So the general thing that we're trying to develop here is a geome that draws springs, like the curly bouncy things. And the one piece of information that I didn't really understand when I was starting to read this chapter is that we're basically we're trying to draw springs as if they were points. So if you picture your data set that has maybe like an X column and a Y column or something, it has like um, a column for like a categorical column that you might end up using to color things. Basically, you'd be drawing one spring object per row of your data frame. That was not immediately clear to me at the beginning of this chapter, and it becomes relevant later. So I just wanted to like set that up, just like you might draw one point, you're going to draw one spring. So there's 5 stages of this process. I'm going to go through as many as I have time for, which is we're going to first start with using geom path and creating a new stat to draw our spring. And then we're going to allow diameter and tension of the spring to vary. And then we're going to convert to a geom instead of a path. And then we're going to draw the spring with a grid instead of relative to the data. And then we're going to talk about adding custom scales and legends. So we'll see how far we get. I may gloss over some of the details because there were a lot of details, but hopefully we'll hit the main points. Okay, so stage 1 of this process is to develop a new stat. So first we have to draw a spring. I'm not going to go into the details of all the code that's being used here, but the general idea is that first we draw a circle and then we stretch that circle along the x-axis to look something like this. I would not have been able to come up with this myself. I think it's pretty clever. Basically what they're doing is just adding a set amount to each like adding a little more each time to each X position so that as you progress along the circle that's being drawn, it gets shifted more and more and more. And this is only one revolution of the spring, but the idea is that you could keep doing this and you're creating an object that basically looks like a spring. And as a nice little addition, they have added an alpha that changes throughout the spring so that it looks like it's actually being drawn with a hand, which I thought was kind of cool. So there's 2 main parameters that define the spring. There's the diameter, which is how big is that circle, and there's the tension, which is how much we're stretching the circle. And it's important to know those parameters because we're going to need to make them arguments of our functions that we define later. So how do we decide whether to use a stat or a geom? They talk about how you can use a stat if the thing you're trying to represent can be basically an existing geom with transformed data. And that's exactly our case where we're drawing a path, but instead of like going straight, it's circling around. So it's just different data, but it's still fundamentally like it is a path, right? It's still a line that's being drawn. It's not some different thing. So that suggests that we're able to use a stat, which is simpler to code than a geom. So we're going to be developing a stat, and then we're going to use geompath to actually do the drawing of that stat. And then as we'll see later, there are some limitations to the stat that can be addressed by converting it to a geom. Okay, so the general strategy is that we're going to make a function to draw the springs, and then we're going to incorporate that function into a ggproto object, specifically a stat. So we'll start by making the function. Oh, my bullet points got messed up here. Sorry about that. We're going to make a function called createSpring. And to think about just the arguments we're going to need for that function, we're going to need a starting point for the spring defined by x and y coordinates, and then an ending point for the spring because the spring has some, length. So that's going to be defined by x end and y end. This is similar to like geom segment or other types of geoms that we've seen that have two different points that define them. We're going to need the diameter, which is the size of the circle, the tension, which is how stretched it is, and they define it as how far the spring moves relative to the size of the circle. And you can define that as the distance from the start point to the end point divided by the diameter of the circle size. And then also resolution, which is sort of like the visual fidelity of the spring, how many points you're using to draw the circle. We'll use the parameter n to define that. So we put all of these arguments into this function called createSpring, x, y, x end, y end, diameter, tension, n. You'll notice that we've set these to absolute values right for now, and that will change later. But yeah, so that's what we do. We do some validation of the input arguments, which I'm going to skip over for the sake of time. We're going to do all the calculations, blah, 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 create a data frame. And notice here that we're returning a data frame. That's going to be important later. The createSpring function really is creating a data frame of x and y points, which will ultimately be connected by a geom path, but that those points are sort of along the trajectory of the spring. So some important things that this function does is it precisely defines its parameters, it checks the inputs, and it throws an error if the inputs are invalid. That's really important because it will allow this geom to be robust to user input. And then it also does not depend on dplyr. This is something that I've encountered before when I'm developing stuff, like because I mostly code using the tidyverse, when I'm coding functions, it's very tempting to depend on other packages. And that's not inherently bad, but it is like worth thinking about what dependencies you want to have. So here they've done everything here in base R, which is actually not too bad because this is pretty simple code, but everything's in base R, which means that this geom will not need dplyr to run. Okay, so we can test out createSpring to make sure that it works. We pass in our various parameters here, and we plot the spring as the data set. So spring is the data frame that's returned by createSpring, and we use geompath to actually connect the points that are output by geomSpring. And we use coord equal, a little bit more on that later, but for now we're going to keep our coordinate system equal so that the circles actually look like circles. So we've defined a spring, and it's beautiful. It looks like a spring, sort of, which is awesome. Okay, so we're going to now create a stat. Recalling what we learned in chapter 20, or in my case, not particularly recalling what we learned in chapter 20, but relearning the same content now, we're going to start by creating a subclass of stat called stat spring. And we do that by first defining stat spring as like a ggproto called stat spring, and it's a stat. This is just naming the class. And then we can take a look at the stat object in general and look at what are the various methods, the various like properties in here that we theoretically could modify. I don't understand all of these. We're only going to be focusing on a few of them. And they, excuse me. Also, I can't see the chat, so please do speak up and stop me if you have questions. Okay, so they do mention that we should not touch aesthetics and parameters. I don't really know how we're supposed to know that. It sort of seems like this should come it should come with a thing that says like do not touch. But I guess maybe we should operate on the principle of like, let's just not mess with anything unless we know for sure that we want to mess with that thing. And in this case, we're going to be messing with just a couple of the properties. Specifically, we're going to modify 3 methods or fields: setup data, compute panel, and required AES. So this is the entire code here of the stat spring ggproto object. And in a minute, we're going to go through what's going on here. But I just want to identify that there's three parts to it. There's this setup data place, method section. There's the compute panel section, which is all of this. And then there's the required AES section. So let's go through those three and explain what's going on. So the compute panel method, we talked about this in one of the previous weeks. You always have to have a compute method defined. So that's usually compute group or compute panel. And compute group is for when your stat operates on multiple rows. Compute panel is for when your stat operates on single rows. This is where I got confused, and that's why I told you guys at the beginning that the idea is we're defining one spring per point, essentially, one spring per row of the data. They made that assumption, and I was like, oh, okay, I didn't realize that, but okay. So in this case, we know that each row of our input data frame is going to be generating one spring. So compute panel is the appropriate choice here. So in our compute panel section, this is just the same, this is the chunk of code from the previous slide that I've just copied over. And our compute panel method here, we loop over each row of the input data frame and create a spring that corresponds to that row. And then later we're going to be adding the other columns back to the computed data. So basically each row of the data frame is going to become many rows because it's going to become sort of like all the points that make up the spring. And then we're going to need to add back any other columns that were present in our original data that might be really important later. So for example, if you had like a type or a class or some other categorical factor that's associated with each spring that you might later want to map onto the color aesthetic, for example, that information needs to be preserved. And then finally, we use rbind at the end to return a single data frame because lapply generates a list. And that list will be like a whole bunch of data frames, one for each of the springs that we're generating. And we want to then squish them back together to get one single data frame. So first we take our calls to keep, which is all of the columns in our data frame except for the X, Y, X end and Y end columns. So that's how we grab all the other columns that we're going to need to squish back on at the end. And then we go through using lapply, we go through all the rows of the data. And for each of those rows, we use the create spring function. Remember, the create spring function takes in, each of those 4 parameters. And here they're being pulled from the corresponding row of the data. And it also takes in a fixed diameter, tension, and n that is specified in the function itself. And later on, we'll see how we can modify that. So as you can probably imagine, this chunk of code generates one data frame that has as many rows as n is. So as many rows as we need dots in the resolution of the spring. And then it returns that spring path object. And then we can bind on the columns to keep. So that's all the other columns, attach that to the data frame. And then after that lapply call, we end up with a list of data frames and we bind all of those data frames together and return that from the overall function. That gives us our broader data frame. How are we feeling about this so far? I know I'm going really fast. Anybody have questions that we need to pause for? Okay, cool. All right, so what's going on with the setup data method, which was also included in that stat. So setup data sets up the data. I don't deeply understand this, but here, this is what it looks like. This is what that portion of it looked like. And basically what this is doing is making sure that every row of the input data is its own group. That's because geom path, ultimately, which we're going to use to draw this data, is going to need a unique ID for each spring so that it doesn't like put connecting lines between the springs. So here, this is just saying if there if there are any duplicates, we've got to create a unique ID. And something that's interesting to note here is that the way that they create a unique ID is not just by erasing the groups and replacing them with like integers 1 through n row or something. It's actually by taking the existing groups and then pasting on another number with like a dash as a separator. And that's important because the group structure might contain important metadata. Like the actual content of like what you grouped your data by might be really important later on. We're not going to come back and talk about that, but they were saying theoretically that's information you might want to use, and so it's worth preserving. Okay. And then the required AES field, this is more straightforward. This is just saying which aesthetics are mandatory, which aesthetics does the user have to provide. And in this case, we need X, Y, X end, and Y end, and the others have defaults, right? The diameter, the tension, and the N have default values, so the user does not have to provide them. Okay, so we made our stat, and now we need to make constructor functions. So we can, because we created a stat, not a geom, we could just use geom path with stat equals spring and be done. But typically we add a matching geom function because it's easier for users. And I think this is interesting to reflect on because I remember at the beginning of this book, I did not even know that this was a thing you could do. And I really didn't understand the difference between geoms and stats. And I'm definitely still like learning that. So I think, most users who use ggplot are using it through the geom underscore whatever path, and stat is kind of an advanced use case. So we might as well make this easier on our users by adding a geom function. So in this case, we create this wrapper function, this constructor function, which I won't go into super detail on, but just note all these arguments here, which are specifying some of the line parameters, and then it's got a call to layer inside. That's the main meat of like what's going on is it's creating a layer. We've seen this before, and it just specifies the identity stat, but then it specifies which geom to use, and it gives the parameters that we just passed in up there. And then we're going to make a stat spring function. So this is a direct analog to the geom spring function, except instead now we're specifying the geom, which is inherited from here, but then the stat is the stat spring object that we just created in the previous portion. So these are the constructor functions that actually like make the layers that the user will interact with. Okay, so testing out how this works, we make some fake data. In this case, we're making 5 rows of data, so we're going to end up with 5 different springs. And notice that we also have a class column, which is a categorical, which we'll use for coloring later to illustrate how that works. We use that data with ggplot with passing df in as the data set and using geom spring. And we tell it which columns to use. Now, in this case, our columns are actually called XY, XEnd, and YEnd, but they could be called something else, and we just use our aesthetic mappings to tell ggplot which columns to use. And we're still specifying chord equal because we want our circles to look reasonable. And this is what we get. So it's a little hard to see, but there are actually 5 springs here. There's 1 here, 2, 3, 4, and 5. And we can also use our built-in methods without any further work. We can do some faceting, and we can do some coloring by additional variables because we preserved those variables when we were creating our stat. So here's what it looks like if we color and facet by the variable class. So this is like pretty functional, right? Like this is not, we didn't do a ton, and this basically works. The rest of the chapter goes into like how you can make it better, which is what we're going to talk about now. But like what I thought was cool is this basically works. And you could use this as a blueprint for, I don't know, I can imagine lots of like fun implementations for wanting to create like your own cool like objects that then get plotted. This would be fun for like generative art. This would be fun for I don't even know what the applications could be, but it just seems like, if you want to plot some arbitrary stuff on a grid, that goes a little bit beyond just substituting something in for one of the plot characters. This could be like a really cool thing to do without too much work.
Do you think this could be for, like, for example, I'm going to make something up, which I'm pretty sure
Yeah.
someone has already done, but you know how, so ggplot has their own box plots, right? And they have a way of putting, for example, the median in the middle,
Uh-huh.
and
Oh,
the
yeah.
little box, etc. So let's
Yeah.
say, which I'm pretty sure someone else already made a package, but let's say internally
Yeah.
you don't like that box plot and you want to add the median and the mean. I'm doing a
Yeah, that
very
sounds like a
simple
great
example.
idea. Yeah.
So you want already a GM that's already been done, but you want to
Yep.
customize it to your own liking.
Yeah.
So I think
I think
that
that's
this
a
is a
great
way of doing
example.
that, right?
Yes. That's a much better example than what I was thinking of. And that's something I've wanted a lot actually. So I think that's a really good idea. Yeah, that would be an interesting challenge. Like one thing that it would be cool to, I mean, I know we're about to hit Christmas, but like theoretically for these book clubs, it could be interesting to build in some like lab sessions where we all work together on doing something. Like it could be cool for us to work together on trying to make that happen. Just as an exercise.
You should
Yeah.
put that suggestion in the on Slack and then
Uh-huh.
tag John and see what
Hmm.
he says about it, because that could be like a post book type of
Right.
situation. Like, we already finished it. Now let's do like a, I don't know, advanced
Yeah.
book finishing or something. Ashley, you wanted to say something? I'm sorry I interrupted.
No, no worries. Yeah, I was just gonna say, like, I could definitely see doing stuff like this for like running like growth curves. I have to use stat function to like pull the function that I have
Mm,
for the equation for the growth model, and just packaging it this way would just make having to do that repeatedly over and over in the code just like less work.
yeah. Yeah, that's a great point. Lots of good applications for this, and also very silly ones. I mean, I think the spring one is a very silly application, but it illustrates a lot of their concepts really well. So yeah, it's neat. Okay. So moving on, you could alternatively use stat spring directly. That's one of the strengths of creating a stat. Um, and this broke my brain a little bit, but I'm just trying to remember the differences between stat and geom. So if you wanted to draw the springs with something a geom other than path, so what's happening in the underlying data, right, is that it's generating a whole bunch of points. But and in this case, we specified n. What was n by default? N was 50. So by default, we're specifying 50 points. So each of these springs is like defined with 50 points, I guess. Although that actually seems low. So maybe, I'm not sure. But anyway, if you wanted to instead draw them with points instead of lines, um, here we're using stat spring directly and we're using geom equals point. So instead of smooth springs, we're going to get like dots, right? And in this case, they've reduced n to 15 so that we can see this more clearly. So I guess, okay, I guess it must be number of points like per revolution of the spring. I don't remember how the underlying code was written, but yeah, you get the idea. So that's what that would look like. And that's thanks to the flexibility that we get from using a stat. Okay, so we have some limitations here, which is that diameter and tension are currently defined it like layer wide. So all the springs in the layer are going to have the same diameter and tension. And it might be really nice to map those parameters to values in the data so that you could have like a bigger spring or a tighter spring or whatever based on the actual value of a variable, just like you can for most other geoms. So now we're going to talk about how we can modify what we've just done to make diameter and tension their own aesthetics so that they can be mapped to data. Okay, so first we're going to go back to our stat spring, ggproto, and we're going to modify compute panel to add diameter and tension as aesthetics. So what I've done here is I added comments to show what this used to look like. So we haven't changed anything about our setup data portion. We're still doing this like modifying the group labels. But now in compute panel, previously we had diameter and tension as direct arguments to this function. And now instead, we are taking them from the data, just like we're taking the x, y, x end, and y end from the data. So they will be variable by row of the data. And I guess I'm a little confused about why this part doesn't change. The calls to keep. Because here you're assuming that there's an x, a y, an x end, and a y end in the data. But here you seem to be requiring that there's also a diameter and a tension. So I'm not really understanding why those are not taken out here. It's possible I made a mistake, or it's possible that there's something that I'm not understanding. But I think we're going to move forward because we don't have much time. We're already halfway through. So we do much the same thing here. We add back the calls to keep, and then we bind it all together into a data frame. And the other thing that we're adding here is diameter and tension are now optional aesthetics. They can be specified globally still, or they can be specified by the user to be mapped to the data. Okay, so now we're going to change the constructor functions to remove the diameter and tension arguments, which were previously like directly passed into those constructor functions. So instead of, again, I've put comments here. Those used to be there. They're not there anymore. That's what the geom spring constructor function looks like. And then and we haven't made any changes here. And then for the stat spring constructor function, same thing. It used to have direct arguments for diameter and tension, and now those are gone. All right, so testing out the new implementation. So now we are creating a data frame with the same stuff as before. We've still got this class column, but now we also have tension and diameter columns. And again, theoretically, these could be called something else. And I actually think it would have been potentially more interesting if they had created fake data with different names here to show like mapping tension and diameter to something meaningful. But they didn't, so here we are. And I didn't have time to change it. Okay, so this looks pretty cool, actually. Now we are adding geom spring with AES, tension equals tension, diameter equals diameter. And so now we have different springs with different diameters and different tensions, depending on the value that is present in that row of the data. So again, cool potential for art. You could like draw a scene of maybe like a mechanic's shop or something with a bunch of springs on the floor. The things you can do with code if you have a lot of free time on your hands. It's amazing. Okay, so the problem is now that we have that nice flexibility with diameter and tension, we can't set it for the entire layer like if we want to. If we try to do something like this where we set diameter outside of the aesthetic mapping, like we're used to being able to do with color, for example, we can't do that. And that's maybe not a huge problem, but it's partly a problem because it behaves, this is not behaving how you expect it to be behaving. I'm thinking about alpha, for example. This is something that I often end up with, you could map alpha to values in the data, but more often what I want to do is just set the alpha of all points in a layer to like 0.2 or 0.5 or something to make everything transparent. So I do that outside of the AES parentheses in that layer. And here they're showing that that sort of thing is not possible here. You get an error, or you actually get a warning, and then you get a blank plot. So that's not great. So in order to fix that, instead of using a stat, we need a geom. Typically, when you're making your own extensions of ggplot, the stat approach is enough. But in this case, we have some parameters that need to be expressed in units that are not related to the coordinate system itself. So it's time to rewrite this geom to be a geom extension instead of being based in stat. Okay, so let's do that. The difference between stat and geom, which again, I'm still trying to wrap my head around, is that stat returns the modified data, which is then passed to a geome to be drawn, whereas geome returns an actual graphical object. So if we go back a little bit to this stat spring definition here, the ggproto, we notice that that the thing that's being returned in compute panel is this thing. It's not super clear because there's not a return statement, but it is this part here where we have bound together all those data frames into one giant data frame that has the data to draw those springs. And that's what's getting output here. But then it needs to be given to the geome to actually, like, with the path method underlying it, which is what we did in our constructor functions, to actually be drawn. And so now we want to make a whoops, where did it go? We're still on this one. Okay, cool. We're going to make a geome which is going to return the actual graphical object instead of the data itself. So just like we did with looking at the stat ggproto, now we're going to look at the geome ggproto. And as before, we have many different methods in here that not all of which I understand. We're going to ignore most of these. I assume, as before, we should probably not touch aesthetics and we should probably not touch parameters because those are supposed to be internal only. But we're just going to do what they tell us to do here and create the geome. So instead of compute panel, we now have draw panel. And that's because we're going to create the data object and then we're going to pass that data object called springs into geompath $, excuse me, into geompath $, draw panel to actually create that graphical object. We're also going to use default AES to set the defaults. I don't really understand that part, but I just wanted to note that it's there. I don't really understand why that's different than what we were doing before with the stat. So the setup data is much the same. There's a little bit of a difference, but we're not going to bother with it right now. This is the most important part. So here we have this draw panel method, which is replacing compute panel. And first we do the same thing that we saw before. So this is familiar. We have our columns to keep. We generate our springs data object, which is going to be the output here is going to be the bound data that's just like a long data frame. And then we have an extra thing here where we're going to use the draw panel method directly from geompath to take that data set that we just created and take all the panel parameters that were specified at the beginning of this this geome and actually generate a graphical object that is the output. Now, again, it's not super clear because there isn't like a return statement, but the result of this is what we're returning instead of returning this. So we're returning a graphical output instead of returning the data set that underlies it. And then we also specify the required aesthetics as before, and now we're also specifying some default aesthetics for that graphical object. And I think what's going on here is that the graphical object needs certain aesthetics in order to even make any sense. And so those aesthetics, we have to tell it like what to use by default, I think. I barely understand what I'm doing here. So now we create new constructor functions now using geom spring instead of geom path. So geom spring is the geom that we just created right up here. And otherwise these look basically the same. So I'm not going to go through the details, but so we've got our geom underscore spring constructor function with our layer inside. This is the part that changed, right? Now instead of geom equals geom path, we have geom equals geom spring. Same thing with the I guess we don't need the stat spring because we are not using the stat anymore. We're using geom. So yeah, we used our geom spring constructor function, and that's what the people are going to be actually interacting with. All right, let's test it out. So now we have geom spring with tension and diameter able to be modified by columns in the dataset. I guess I didn't include the part where I was generating the data frame. Whoops. But I think it's the same one as before. So that's cool. It works. And sorry, we saw this before. My bad. We were previously able to modify tension and diameter. What has changed is that now we can also set diameter globally in the layer, layer wide, and not have it be mapped to the data. So we have the choice. Whereas in the first implementation, we had to set it layer wide. And in the second implementation, we had to map it to the data. Now that we have a geom, we have the flexibility to either map it to the data or not map it to the data, which is pretty cool because I can definitely think of use cases for both of those things. Yeah. Let me pause here for a second. How are we feeling about this so far? Does anybody want to ask questions or go over anything? Seeing a thumbs up. All right, cool. So we still have an important limitation, which is that diameter and tension are in units relative to the scale of the data. And we can see that that becomes a problem when we have different axis like ratios, right? So different, we'd been previously specifying chord equal, but in this case, we've got our x going from 0 to 3 and our y going from 0 to 20. And we end up with a spring that's like totally stretched out. Now, maybe that's what you want, but in our case, if we want a geom that behaves kind of as expected, which is that you're putting these spring objects onto a grid and expecting them to look somewhat nice, we would ideally like for that width, that diameter to not stretch with the plot, to be something independent of the graphical viewport that it's plotted on top of. This one I understood less. Let me pop over to this for a second because okay, so yeah, the same underlying problem means that the diameter of the spring is expressed in coordinate space. This means it makes it difficult to define a meaningful default because the absolute size of the spring diameter changes when the scale of the data changes. Yeah, so I think what they're trying to show here is that when the scale of the data goes from like 0 to 100, now the spring inherently is teeny tiny because the diameter, the default diameter we were passing in, I forget what it was. It was like 0.5 or something like that. And so now it's a teeny tiny spring. And so it's just another way of showing that it scales with the area of the plot instead of being independent of that. Okay, so to fix this, we're going to use a grid grob. And this is where I start understanding a little less, but we're going to do our best. So what is the grid package? In base R graphics, they have what's called like a pen on paper model, which is that each portion of the code that draws the plot is literally like drawing a portion of the plot directly. So it's like you have a paper and then you draw one thing and then you draw another thing and then you draw another thing, and that's sort of how you build up the plot. The grid package builds up a description of the graphic as an object, which is later rendered in a separate step instead of rendering each bit of it like one at a time. And that means that grid objects exist independent of the graphic device. They can be created separately, sort of like a ggplot object, I guess, where the object itself is a thing, and then as a separate step, that entire defined object is drawn. That also means that parts of it can refer to other parts. So for example, if we wanted the size of something to be set to be relative to the size of a different part of the grid object that we already defined, we can do that. The parts can refer to other parts, which is really useful. So in this case, we need graphical objects relative to the coordinate system, but with some parts that have an absolute size. And that just definitely describes our use case for the springs. We need the springs to be responsive to the coordinate system, but we would also like to be able to set things like the diameter to some absolute size, so if we want to, right? So that it doesn't always scale with the the plot, and so that it doesn't get stretched weirdly if the aspect ratio is different. Okay, so we're going to go over some terminology from the grid package which will be relevant later. So a GROB is a graphical object. I think it's such a funny word, but I'm, kudos to them for determining that that was what we were going to call them. And there are several GROB functions in the grid package that correspond to the different types of graphical objects. So for example, points GROB or circle GROB or lines GROB. Here's an example. We load the grid package, then we create a circle GROB with several different parameters, X, Y, and R. So I guess X and Y are the positions of the circles and R is the radius of the circles. And what this example is trying to point out is that all of these GROB functions are vectorized. So the circle GROB creates more than one circle. I was confused by why it's not circles GROB. It's not. I don't know why. It is points GROB, plural. That's not a typo. And it's lines GROB, plural. But it's circle GROB, singular, even though circle GROB is also vectorized. So I don't understand that, but whatever. And we can see that when we look at the circles object, this is what it looks like, right? I don't really know this syntax. Like, I don't know what 582 means, but it's a graphical object which has some internal structure that exists independent of the plot that represents that graphical object. And that's the important part here. If we want to actually draw that object, the way that we do that is we first ask for a new page to draw the object onto, and then we use grid draw to draw that graphical object. And this is what it looks like. We've got 3 circles with 3 different centers and 3 different radii. There's also a function called GROB tree. I don't really know why isn't it called GROB combine? But anyway, so if we make another GROB using text GROB, and again, we can see this is vectorized. We've got small, medium, and large. We've got the 3 X positions, which are going to correspond to the circle positions. And then we generate a composite using GROB tree. Then that gives us a GROB that is a combination of the 2 other GROBs that we just created. I didn't include a part where we typed the name of composite to actually look at what's going on under the hood, but I assume it looks somewhat similar to this, except that it's got multiple GROBs. And so once again, we're going to create a new page, and then we're going to draw this composite. And you can see that now we have the text and the circles that get drawn together. Okay, so another important term is a viewport. So the viewport is the rectangular plotting region with its own coordinate system that you're drawing your objects like into or onto. And viewports can be used in complicated ways, which we're not going to get into. They mentioned briefly that you can embed a viewport within another viewport, for example. I don't know why you'd want to do that, but cool. In this case, the example they chose to illustrate this is that the viewport can have an angle, it can have different dimensions. So in this case, we're creating one default viewport, which is just a blank viewport, and then we're creating a rotated viewport, rotated by 15 degrees. So now we're going to use GROB tree to once again combine circles and labels and define the viewport in that GROB tree. So now these GROBs that we're creating, the composite default and the composite rotated, inherently have a viewport associated with them. So instead of being drawn onto the default viewport, they're going to be drawn onto whichever viewport we specified here. So once again, we'll create grid new page, and then we're going to draw 2 different GROBs on the same page. So I guess this is why you have to refresh the page, right? Because each one is going to be drawn onto the current page, sort of like opening up a graphics device and then base plotting and then using dev off. So here is the default, and then on top of it, we're plotting the rotated composite. And because that has its own viewport associated with it, it's going to be rotated 15 degrees like we specified. Looks like the ordering of the layers works the same as in ggplot as well, probably because ggplot is sort of built on this under the hood, which is that the second thing comes on top of the first thing. All right, then graphical parameters. I thought this part was cool, which is that the function gpar specifies graphical parameters actually as their own objects. And so here's some examples. We can create a graphical parameters object with a blue color and a graphical parameters object with an orange color using the gpar function with the color argument. And I guess you could also have the fill argument. I'm not sure like all the different things you could put into gpar, like what the possibilities are, but this is just one example. So in this example, now we're going to create 2 new grobs using grob tree to combine things. And we're combining circles, labels, specifying the viewport, and now we're adding the gpar object, which passes all of its graphical parameters into the grob. So if we draw both of those on top of each other, now we have the same thing as before, but the first one has taken the blue graphical parameters, and the second one has taken the orange. Okay, another thing we have to understand is units. I clearly do not understand how to use Markdown because all of my lists keep getting squished, so sorry about that. So when we need to specify the positions of things, and this is going to be important, we can do that in various ways. So there's absolute units, which are like centimeters, inches, points. Then there's relative units, sorry, which I think we've maybe seen before with this NPC argument, stands for normalized parent coordinates. I had to look that up. And that's the proportion of the viewport size. So it's the size relative to whatever viewport you've defined. And then we also can have, as I referenced before, we can have units that are relative to other parts of your graphical object. And I don't fully understand this part, but yeah, the units can be defined relative to the width of the grob or relative to the width of a string. And this is kind of a cool, sorry, there's just a loud noise. I'm hoping everything is fine. Operations are resolved at draw time. So what this means is that, as with everything else with the grob, we're defining the entire object first, and then we're going to draw that defined object. So that means that you can combine different types of units. For example, here, we have this thing here is half, like 0.5 of the normalized parent coordinates. So that's going to be the center of the normalized parent coordinates. And then we're adding 1 centimeter. So that this was relative units here, and this is absolute units here. And so combining the two gives us a position that is 1 centimeter to the right of the current viewport, of the center of the current viewport. The part that I don't understand here is why this can have 1 dimension. Like, why do we not have to specify 0.5 width and 0.5 height? Does anyone know more about grid than I do? Okay. Gabby? We can't, you're muted.
But if it's grid, it's a square. So I guess height and width would be the same. So they're just,
yeah, so I guess they just assume that it's the same. Yeah.
I think so. Yeah.
I guess so. All right.
I wonder if like there's a way to specify both, but if you don't specify both, it assumes that they're equal.
That would make sense, like a default.
Yeah.
Okay. All right, so I skipped the next 2 sections because I was running out of time to make the slides. Actually, I think we're just going to go back to the chapter at this point because my slides start to break down. So let's go down to, yeah, so I skipped the building grob classes and the tabular grid sections for the sake of time because they seem to be telling me that they were not super directly relevant to what we were about to do. So let's skip those and we can return to them if we want, but we only have 10 minutes left. So let's actually just go to the part where we're creating a grid grob. And so the first thing that we do is we define the spring grob function. And we notice here that we're doing a lot of stuff with units. We're specifying defaults in relation to the size of the viewport using these NPC units. I really wish it was something other than NPC. I'm not going to be able to remember like that is what that means, but whatever. We still have informed defaults for tension and N. Default units are NPC, so by default we're specifying everything relative to the current viewport, but we can change that if we want to. We have some null gparse some empty graphical parameters, but this implies that we could pass in a whole bunch of different graphical parameters if we wanted to, and a null viewport as well. So if the user doesn't specify the unit, we're going to use our own. We're going to use our defaults. And then this is the main part of this function. So this is really not much going on. This is just a wrapper. The spring grob is a thin wrapper around gtree, where gtree here is returning a gtree of class spring. It looks like we skipped an important section here, which was what gtree actually is, because we had grob tree before. But what is gtree? Huh. Oh, okay. So the first step is to write our own constructor function using grob or gtree. Okay, so I guess gtree is if we're creating a composite object. I don't really understand how that's different from grob tree. Does anyone else understand how that's different from grob tree? Okay, we're just gonna assume that that is conceptually similar to grob tree. Cool. Skipping that. Okay, so this is the main part here where we're taking all of these different parameters that were specified up here that had their units transformed if applicable, and we're calling the class spring. Okay, so yeah, all it does is ensure that the arguments are converted to units if necessary and returns a composite grob with class spring. But this didn't actually like draw anything, right? It just returned this grob with a class, but there's no section in here that actually does the creation of the springs. So that's what we're going to do now, which is to define part of the make content method. And so it's the spring method for making content, I guess. So here is where we actually use our create spring function. This part should be familiar. Once again, we're using lapply to go along the entire data. We're creating our springs. We're binding those all together into a single data frame. And now we're using this polyline grob function to actually construct the spring paths as their own grob. So this is the more important part as well. And they're saying that nothing too fancy is happening here. When the plot is resized, we grab the coordinates in the diameter settings and convert them all to millimeters. And yeah, so they're saying by pushing the call to create spring to this level, we can ensure that the path is defined using absolute units and then return the result as a polyline graph. So it's basically able to take information in about the current state of the plot area and use that information to figure out what the units need to be in absolute terms, and then generate a graphical object that will match that, which is why this is so like flexible and can take in our own relative units, convert them to absolute, or it can take in our desired absolute units and keep them absolute. Okay, so I didn't totally understand what I just was talking about, but that's a surface level understanding of grid and grobs, and we can see that we can draw this. And importantly, here we can specify our diameter in units of centimeters, even while specifying the other stuff in relative units, which sure enough allows us to draw two springs of drastically different sizes. Okay, we have 5 minutes left, and I'm going to skip the part where we create the next geom spring, but sort of TLDR, we are now doing this. We're creating a new geom that actually has a GROB underlying it, which allows the new geome to have that power to accept absolute units. Go back and read this part. It's very interesting. We just don't have time. And then we're creating a new geome spring function that again calls a layer that uses the new geome spring object here. And now we can properly use this geome spring function. And now this will have all of the functionality that we need it to have. It can be flexible to the size of the plot. It's not going to skew weirdly when the plot dimensions change. It can accept either mapped or constant values for diameter and tension. And it can take, different diameters as well. Okay, cool. So that's what we wanted. We've created a nice geome spring. They're pointing out that there's some other changes. In the last few minutes, I just want to point out what we're doing with scales and legends as well. So the reason this is important is because we have two new aesthetics called diameter and tension. We previously had X, Y, X end, Y end, and we've got, our usual color, whatever. But because we might want to map variables to diameter and tension, we might also want to scale those variables, like scale diameter manual or scale diameter discrete or continuous or whatever. So we need to actually create these new scaling functions. And we discussed this already in chapter 20, but we basically have three possible fundamental scale constructor functions, either continuous scale, discrete scale, or binned scale. So we need to write wrappers to go around those, any of those three functions so that this will work. So scale tension continuous is a wrapper to continuous scale, and all we're doing is adding the name of the aesthetic and adding a palette and rescaling to the range, default range here. And then we also create an alias for scale tension continuous because it's always going to be continuous. We don't need to separate those. And scale tension discrete, if anyone tries to use that, we're going to throw an error because you can't scale tension to discrete data. It just doesn't make any sense. We're also going to do diameter, which is a little bit more complicated, and we're not going to go into it, but this is a typo, it looks like. This should say scale diameter discrete. Maybe I should make a pull request for that. Anyway, so now we have lots of options where we can map the diameter and tension to the data, and we can apply some scaling and create some really crazy stuff. Awesome. So this legend isn't very helpful because we haven't specified our own legend function to make the legend actually look like it should. And so we need to create a custom legend key function. I really do not have time to go over this. I have another meeting at the hour. So I think I'm going to leave this as an exercise to the viewer to go through this part. But the general point is that we're going to create legends that actually represent springs, which is pretty wild and, debatable how helpful that is. But that's shows you the process. All right, we made it. The takeaway from this chapter is you can do a lot of stuff extending ggplot. My takeaway from this chapter is I'm not going to remember most of this, but if I ever need to actually extend ggplot, I'm going to walk through the steps in this chapter and try to actually do them. So yeah, if we're interested in doing that together at some point, we could. This was the last chapter, so yay. Thanks everyone for being on this ride together and for getting through such a big book. I think it's been very instructive.
Yes, thank you, Kaija, for walking us through this one. I think this was probably the most difficult chapter out of all of them. So we're gonna finish now because I know you have to go to another meeting. Thank you everyone for being here. Cohort 3 is officially over, done, and we finished the book. So yeah. I think, there are going to be a few more things to do, like the Lin Pedersen talk that's going to happen in January. I think John is going to keep us updated on that. So everybody have a lovely day, and I will see you all in 2025, hopefully. Bye.
Bye, everyone. Thank you so much.